You could use other transactional mechanisms like a Zookeeper that provides you the kind of distributed consensus mechanism. But again, these are heavy mechanisms, and we're often looking to something that is very lightweight. And this is what CRDTs provide. It's effectively a concept, or these are the data types that provide strong eventual consistency guarantees. Which means that, so what is eventual consistency? That means that if you have replicas or services, and eventual consistency tells us that those systems would eventually converge to a single state or the consistent state once all the updates ceases, once all the updates to the system stop. Now, strong eventual consistency is something stronger, and it tells us that as soon as all the replicas receive the same set of updates or events, they will be in a consistent state. So that is stronger because it does not require all the updates to the system stop. It's slightly stronger, and again, it does that without the coordination, or with a heavy coordination. There are two types of the CRDTs. There is commutative replicated data types, which propagate operation. So, for example, if you have a counter, you propagate operation like add or remove from the counter itself. So counter may be a kind of shared state, a type of CRDT. There's so these are commutative. These are, I think, converging RDTs where you propagate a state. So the state of the counter itself, for example, you propagate it across the system. The difference there is that so the commutative RDTs are commutative but not idempotent, which means that the operations can arrive in different orders, or they don't have to arrive in a specific order, but they cannot be duplicated. So you cannot. So operations, events that mark certain operations cannot arrive more than once. So this is So to implement such system, so that CMRDTs, you require a quite the requirements on infrastructure is quite strong. It requires exactly once delivery of those events, of those messages. The advantage is that usually you have less bandwidth if the number of transactions is low, because you just send operation and not the state of the structure itself, which is not the case in the kind of converging RDTs, because it sends the state. So, for example, if your CRDT is a list, you have to send the latest state of the list itself. It provides, as I said earlier, this is a kind of carefully crafted data structure, which means that you have to have a certain types of operations that are commutative and idempotent, or in CDRDTs you have to have a merge operation and update operation, which have specific requirements. It does require slightly less, the requirements on the underlying messaging infrastructure is less. It's enough that it's just a gossip protocol-like messaging would be enough, because the updates can come in any order and can actually be lost as well. Okay, I won't go through that. I would like to jump into a more interesting topic, which is persistence. So how do you handle persistence in the kind of reactive approach, in a reactive model? In traditional architectures, the database serves, you could say that it serves a dual purpose. First one is durability, so to make sure that the state is durably persisted. They're quite heavy, and in itself they are quite heavy. So there's two things that potentially could be separated. And let's have a look why would we decouple those two concerns. So the pattern that it's coming to help us with that is called event sourcing, and this is the way to provide durability to reactive systems. What does it mean? It means that we store all the events that the service generates in response to some commands, and we store those events in an event journal. So we don't persist the state itself. We persist the commands that an actor or service generates. And in case of a failure, we replay all the events. So potentially the node fails. We then instantiate the actor or the service on another node and replay all the events that the previous instance of the actor received, and that means that we have a up-to-date state on the actor that's been just brought up. What is interesting here that it facilitates something I like to call the extreme observability of the system. So you can do you store all the events and persist all the events of the system, which means it can help you with the diagnostics. For example, debug the system or see what was the a sequence of events that led to a crash or a certain bug. It helps you with the simulations. You could potentially simulate behavior of a system. It helps with replication, and we'll go through that later. You could do if you replicate the stream of the events to some other location, potentially a geographical collocation, that could really facilitate that. And then transactions. So that's slightly speculative. There is a Microsoft project called Project Tango that tries to look into that kind of system based on event sourcing and provide transaction on top of the log. Log provides you the ordering of all the events in the system, so you could effectively implement transactions, so rollback, commit, and so on. Okay, so there's small digression there on the delivery guarantees in a reactive system in the model with event sourcing. So you can have an actor without a persistent journal, so you don't store anything. That gives you at most once delivery, because the message can be delivered several times. Sorry. Okay, yeah, you can lose the message if you don't have persistent, so it's at most once, right? Because you may receive the command and fail. And that means, and if you don't have persistence, you cannot repeat that because you don't know what will happen, what led to that, to the event that's supposed to be generated. Actor with a persistent journal, so Git gives you at least once delivery. Messages can be duplicated because you may persist the event, and you may fail because you may fail just before you send out the response event. That gives you so that means that the message will be delivered, but it may be delivered several times. And then we have another guarantee, the strongest one, exactly once. This is the actor with persistence and usual some sort of acknowledge mechanism. So the service or an actor receives the acknowledgement of the receipt and it stores it as well. So when it fails, you can have a look. Okay, I've sent out this message and I don't acknowledge it. It means that I don't have to send it out again. Okay, there's another pattern which is called CommandQuery responsibility separation. So we've seen earlier, event sourcings provide us with the durability, so the persisting all the events that led to a particular state. However, then the question, how do you provide where the query capability starts? Over time, I think 5 minutes. So how do you provide a query capability? And I think there's 3, maybe 4 patterns there. So via the service itself, the state is being held in memory, and the actor can respond to your request to receive that state. So that's one of the simplest approaches. But usually the state there is simple. Perhaps a toggle or some kind of maybe a list of elements. That's effectively what fits in memory and is easily manageable by the actor itself. Then you can have a view service. So for example, you can have an actor that receives events from a number of actors, do some stream processing based on that, and there is I think it was akka, and beyond akka there is a standard called Reactive streams that provide this kind of capability for transforming the events. So effectively you get events from a number of actors and you transform them in some way and store it in your state and then again expose it through regular command and response pattern, messaging pattern. Then there is a kind of third, and I think one of the most interesting pattern or type of exposing the queries and data, which provide, you effectively transform the events and persist them in a database. So you update the state of the database. So this is the kind of more traditional model. And why would you do that? I mean, when you want to provide ad hoc query capability, so it could be a SQL search index or some kind of graph query. You could do that using Actor, but then you have to implement that query mechanism yourself, which usually doesn't make much, it's difficult. Another reason may be that you want to have on-disk persistence. Your state, your database is big and it doesn't fit in memory. It would be difficult to distribute amongst the actors. You have to do some kind of management there, and you don't want to do this, so you offload that to the database. And what is interesting there, so as you've seen there, so we go through we go up from the bottom up to the top of the stack. We go through all those levels of the layers that propagate the change. Now this is the query change feed mechanism. So you want that database to also be reactive. So what do you want? You want to facilitate that reactiveness. You want to have a mechanism called query change feed, and that means that once you retrieve a query from that database, as underlying data changes, you want to modify your results as well. So this is this kind of mechanism that fits well with the reactive model. It's not very popular. I think there's a few databases that support that. RethinkDB, some in-memory stores, caches support that as well. It's sometimes called active query. I think MongoDB has some workarounds that you could implement that. But I think once we go more reactive with our systems, that will be a very popular requirement on the databases. Okay, so what that gives us, the kind of event sourcing secure REST, hopefully as usual is a simplified data flow. The writes go to the log. If you see the left diagram, that's on the left side, the blue thing, this is your log, so event source, the journal. So all the writes go to that log, then get propagated to various different databases that you want to maintain. It could be a search index, it could be your cache, it could be a relational database. And then the kind of gray thing, this is our service layer or application layer, then serves, retrieves queries. It could be also the green double arrow, that's the active query mechanism. So hopefully that's simpler than the kind of traditional mechanism where you have a databases which then, with the system both writes and reads from the same database or a number of databases, that the changes to the databases are somehow propagated to other storage mechanisms, could be an index or some other form like a graph database. So hopefully that gives us the advantage of being simpler in terms of the architecture. It supports diverse query mechanisms, which means that it separates durability from the query, which means that you can have one mechanism for durability, the journal, and then specified storage for different types of queries. And that makes hopefully the whole command and the query side of the system more performant, because command side is only interested in durability, persistence, query on the executing particular queries. Again, extreme observability, I like that. This is where you can do a lot of things with your system. Supports state machine replication. So if you want to have, if you want to migrate the system to a separate data center and do it in a manner that is quite quick, you can do it by leveraging a state machine replication. So effectively sending out the events that affected the system, replicate them, and having a replica on another location. So a couple of disadvantages. It adds latency in simple scenarios. And usually I would think it requires careful design in terms of guarantees and transactions. And we've seen you have to see what is deliver guarantees on the messaging system. If if you want a shared state, CRDTs, and so on, because you don't have that shared state that handles all the transactions and makes things easier. Okay, so I think, so that's the last slide. I have we won't go through the all the consistency models and everything. It's quite interesting in itself, but because of the time here, let's just speculate quickly what would look like a highly scalable platform for hosting or developing the reactive reactive systems and applications. So actors in one data center persist events to a single shared log. I think these days Apache Kafka is one of the best persistent mechanism to serve as a log. And shared log is replicated across the globe using CRDTs. There's a project for that. It's the same guy who wrote Akka Persistence. He's now moving on to provide these to provide this capability of Akka to be able to replicate your system across the globe for different data centers using the kind of CRDT mechanism. Global transactions implemented using shared journal. Again, you could use something like a Zookeeper, but potentially you could use it. You could use the log itself. That's how the databases very often are implemented. The transactions are implemented using the log. It's vertical called operation log, write ahead log, and so on. So there's Microsoft Project Tango. It's still a research project that's trying to do that. Twitter's implemented a new KV store, sort of a transaction consistency type of things using also a distributed log. Then imagine that you have all those events that are flowing through your system, and you want to use the scalable stream processing to run a complex workloads. That will then generate databases to serve different queries, or machine learning algorithms, right? And what fits that well are frameworks like Apache Spark or Flame, Akka Stream itself. It's also an interesting model, not necessarily the big data one, but it's nice. And then then you persist all the storage and views that come from your system, from this processing all the events into a big data platform. So I think this is quite speculative. How would the future platform look like for things like maybe IoT, maybe big financial institution, and so on. And I think that's it from me. Thanks, guys.